Hello students, welcome to chemistry. In this video, I'm going to take you guys through chemical equilibrium, right? I'm going to introduce chemical equilibrium to you guys and give you the crux of it. I'm going to let you guys know about the factors which affect chemical equilibrium, which are concentration when we are dealing with aqueous or gaseous states, pressure when we are dealing with gaseous state, and temperature. And the emphasis in temperature is going to be based on whether we've got an endothermic reaction where energy is absorbed or an exothermic reaction where energy is released, right? Recall your combustion reaction, which are highly exothermic, that releases enormous amount of energy, right? I'm also going to consider the calculations that we do in chemical equilibrium, where we're going to be calculating Kc, right, which is a ratio of the product and the reactant concentrations at equilibrium. And the factors which affect Kc, which is actually temperature. I am also going to look at Chatellier's principle, which states that if a system that is in equilibrium, right, is subjected to a change, if something happens to a system that is in equilibrium, then what is happening is that there are going to be processes which are going to occur which will counteract the imposed change, And I know that's a bit mouthful, but I'm going to take you guys through that. Okay, without any further ado, let's just dive right into it. So basically, before I can give you guys, the crux of this, I first want us to look at systems, right? So if you've got, let's say, a system like this, I never claim to be an artist, right? And then let's say you've got something there, this is an open system. This is an open system. In this system, there is exchange, right, of matter with the surroundings. When we speak of the surroundings, we are speaking about this portion that is outside this, okay? So there is exchange of matter with the surroundings. There is also exchange of energy with the surroundings. So now, when we are looking at a closed system, right? A closed system is a system where there is no exchange of matter with the surroundings. This system is closed, right? So matter will not be exchanged with the surroundings, but energy will be exchanged. This is a closed system. So I want you to take note of this. Stay with me. When we are looking at equilibrium, we are going to be looking at closed system, right? So this system is isolated from its surroundings where there is no exchange of matter with the surroundings, right? Okay. So now, there are different reactions that you guys have been exposed to, right? So you know that you've got, if you've got A plus B, this reacts to form C, right? This is a type of a reaction which we refer to as an irreversible reaction, right? So what this means is that A and B react into completion to form C. You know what I'm saying? So just to take note that A and B are what you call the reactant. And then C here, we call C the product. So now, in irreversible reactions, A and B react to form C, right? And C will not break down or decompose to form A and B. That is an irreversible reaction. So, in chemical equilibrium, we are dealing now with reversible reactions. And as you guys can imagine, what in the world are reversible reactions? We've got a situation where A reacts with B to form C and D, right? It doesn't have to be two things over, it can be one thing, you know? And then C and D also reacts to form A and B. So this is a type of a reaction that is reversible. A and B, so the reactants form products, and the products are converted back to reactants. So this thing is happening, right? It's dynamic. You know what I'm saying? So basically what is happening here is that A and B, which are the reactants, are being used up to form C and D. And then C and D are also going to form A and B. And I want to express this, guys, in a graph, right? Let me define now, what I mean when I speak about, chemical equilibrium. So we have a reversible reaction where the reactants are forming products and the products are forming reactants. During this process, we are going to get to a point, right, where the rate of forward reaction is equals to the what? To the rate of reverse reaction. Right? This is very important. And as this thing is happening, the reactants, right, are still present. So in other words, they do not react into completion. However, there is no further change taking place. Right? So in other words now, we are saying that when we are looking at chemical equilibrium, we are dealing with a dynamic equilibrium where the rate of the forward reaction equals to the rate of the reverse reaction. And at this state, right, the concentration of the reactant and the concentration of product is constant. That is worth noting. The concentration of the reactants and products is constant. When you are at this point in a reaction, you have reached chemical equilibrium, and I'm going to express this using an actual graph. So as this reaction is progressing, the reactants are reacting to form products. That is the forward reaction that is represented by the red graph here. As the reactants are reacting to form products, right, they are going to get to a point whereby the rate at which these products are being formed are going to equals to the rate at which the products are reacting to go back to the reactants, right? So that is the reverse reaction. So initially, there are no products. The reactants are reacting to form products, and the products are going to be converted back to the reactants. It's going to get to a point whereby the rate at which this is happening is equal, right? And also, as I've said, that the concentration of reactants and products are going to be constant, not equal, right? But they're going to be constant, so they are not going to be changing, right? As I've said here, that there is no further change taking place. However, the reactants are still there. So let's take note as to what is happening here, right? So if you look at what is happening here, the reactants are reacting, in this fashion, and then their concentration is decreasing until it gets to a specific point where it's no longer changing, where it's constant. Initially, you've got no product and the reactants are reacting to form those products. So the product concentration over there increases until it gets to a point whereby it is constant. So what in the world are we saying here? We are saying that we're in a dynamic equilibrium, right? Where the rate of the forward reaction equals the rate of the reverse reaction, right? And what we have is that the concentration of the products and the concentration of the reactants, these are constant, not equal to each other, but they are constant. So we say that this is in equilibrium. When we want to find the progress of any reaction, right? A reversible reaction that is in equilibrium, right? When you want to find the progress, that will let us know whether the formation of products or the formation of reactants is favored, we utilize the equilibrium constant, which is Kc. So Kc is the ratio between the concentration of products and reactants in a chemical reaction. Okay, so basically when we've got a reaction, it's just going to be a hypothetical reaction. Let's say we've got X. So X and Y are the actual reactants, and then Z is the product. You know what I'm saying? And then the small x, small y, and small z, those are the what? The balancing coefficients. So we've been learning on how to balance equations from earlier grades. So those are simply the balancing coefficients. So Kc is going to be the concentration of the products at equilibrium divided by the concentration of reactants at equilibrium. So this is your equilibrium constant. That is your Kc. Okay, fine. It is quite important to know, right, that in Kc, the phase matters, right? It is quite important to take note of the phases in your reversible reactions, right? If you've got a gaseous phase or you've got an aqueous phase, right, those will form part of the Kc expression. However, now, if you have pure substances, if you've got pure substances that has got a liquid phase or a solid phase, so those do not have a measurable concentration. These ones don't have a measurable concentration. So what happens now? In the Kc expression, they take a value of 1. So whenever you've got a liquid or a solid phase, these take a value of 1 in the Kc expression. Right? Okay, cool. So if you have the green reaction here, you would realize that this is a solid phase, this is a liquid phase, this is a gaseous phase, and this is an aqueous phase. So because of that, that is a heterogeneous reaction, right? Because the phases are not the same, right? If you look at the blue reaction here, this is a gaseous phase, gaseous phase, gaseous phase, gaseous phase, and hence here we are dealing with a homogeneous reaction, right? So when we are speaking of Kc, Kc for the green reaction, right, it's going to be the equilibrium concentration of the product. So we're going to write it in this fashion. It's going to be A to the power A, the small a is the balancing coefficient, divided by, A to the power A multiplied by B to the power B. We're going to divide this by what? By x to the power x, and then y to the power y. But take note now that x and y are solid and liquid phases, you know, and hence we said that they're going to have a value of 1 due to them not having a measurable concentration, right? So our Kc expression now for this is going to equals to this here. Can you guys see that? Okay, and then eventually we've got the concentration of A at equilibrium to the power A multiplied by the concentration of B at equilibrium to the power B, small b. Okay, so now the Kc expression for the blue homogeneous equation, homogeneous because all the phases are the same, it's going to be the concentration of the product, big A to the small a, big B to the small b, divided by big X to the small x, multiplied by big Y to the small y. You see? So would be able to find out as to what our Kc value is at this point. And take note that Kc is unitless, right? So we're not going to have units for Kc, right? However, it does have a significant meaning, and let's consider that. So if Kc is greater than 1, Remember now we said Kc is going to tell us the progression of a reaction. It's going to tell us whether the formation of reactants or the formation of products are favored, right? So when Kc is greater than 1, that is telling us something. Kc being the concentration of products divided by the concentration of reactants, right? So if this value is greater than 1, let's say it's 2, right? So that is telling us that the concentration of products, this is telling us that the concentration of products, right, is greater than the concentration of reactants. You know what I'm saying? And also, if your Kc is less than 1, right? What does that mean? That means that your products, the concentration of your products is actually less than the concentration of your reactants. You know what I'm saying? And lastly, if Kc is equals to 1, right? That means that the concentration of your products equals to the concentration of your reactants. And we are speaking now, guys, of equilibrium concentrations, right? Okay, fine. So take note. I want you to see this, you know. Let's say you don't even know what Kc means. You don't even know what Kc stands for. For some reason, take note that Kc is a ratio. This is a ratio. So imagine now you've got A over B, right? If you've got A over B that is greater than 1, that means that A is greater than B. You know what I'm saying? So that's why we are saying the concentration of product is greater than the concentration of reactants. If now you've got a situation where this value is less than 1. So now if Kc is less than 1, right? So that is going to mean that the A value is less, right, than the B value. And hence your Kc is less than 1. And also, you know, make sense of it now. You cannot have a negative concentration. You know what I'm saying? Just take note of that. Okay, and then if your Kc value is equals to 1, imagine your A over B. If this equals to 1, what does that mean? It means that A should equals to B. You get that? So that is the meaning of Kc now, that when Kc is equals to 1, the reactants and the product concentrations are the same. If your Kc is less than 1, your product concentration, in other words, less than 1, it means that your denominator, which is your B, is greater than your numerator, which is your A. You know, so take note of that, you know, and also take note that Kc is affected by temperature. So concentration, pressure, or adding a catalyst will not, these ones will not affect Kc. And this is gonna be, you know, you're gonna appreciate this when we are looking at some examples. So this will not affect the value of Kc. Okay, guys, and another thing that is quite important that I want to bring to your attention is you should know how to calculate your concentration. That your concentration is going to be your number of moles divided by your volume. right? And also, you should know how to calculate your number of moles. Let's say you are given, initial quantity, as let's say you're given a mass of something. If you're given mass, you should be able to calculate the number of moles from mass, So guys, we are finally here. Let us calculate Kc. If you're given any reaction, you've got a reaction here which is a homogeneous reaction, because all the phases are in gases, right? I almost said grams, hectic. Okay, so basically, first and foremost, guys, take note of the phases that you are given. You know what I'm saying? So this one is, we have got gases. So gases and aqueous phases have measurable concentrations, except for liquids and solids, So if you've got liquids and solids, right, pure substances, those ones do not have measurable concentrations, and hence, when you bring them into the Kc expression, they take a value of 1, And now, based on the reaction that you are given, let us write the Kc expression. So the concentration of your product is going to be C to the small c divided by A to the small a multiplied by B to the small b. So this is your Kc expression, and in exams, if you get this correct, you do get marks, right? I think it's 1 mark. Okay, so now let us discuss as to how in the world do we calculate these things step by step, because these concentrations here are what? They are equilibrium concentrations, right? And for a number of people, I mean, even I myself was taught this way, and I found it easier, So we used the rise with an extra E method, or the rise table, right? Whichever one is going to help you to sleep at night. You know what I'm saying? So where they are right now, here we are looking about the mole ratio, right? So this is the mole ratio per the balanced chemical reaction. And so if we look here, so we are looking at the small a, the small b, and the small c over there. Okay, fine. And then I here, this is what? This is the starting amount, right? Or the initial amount. These are initial amount. It might be given in moles, right? Of the reagent that are present at the beginning of the reagent present at the beginning. So take note now, guys, that let's say at home, your parents ask you to make them tea, and then you take, the tea bag, the sugar, and all of those things that you use to make tea, the milk as well. So initially, there is 1 tea bag, there is 3 teaspoons of sugar, there is blah, 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 right? But the final product, which is a tea, is not there, right? So you're going to see now that the I there, those are the initial reagents that are present. Imagine that as the initial tea bag, sugar, and the hot water that you will need to make your final product, which is tea, which is not present in the beginning. Okay, cool. And then now we've got C here. C is the change, right? This is the change in the reactants or product. This is the change in the reactant or product, right? And then this change is based on the mole ratio. And I'm going to tell you guys more about that. Remember, when we are balancing our equations, we're going to utilize that, when we're looking at the change. You know what I'm saying? And also, one thing that is important is that the reactants are reacting to form products. So we are going to since the reactants are reacting to form something, so they are going to be reduced, and then the products are forming, so we're going to be adding them. Okay. Anyway, and then E now, the first E, this is what? This is the amount of the reactant or the amount of products that are present at equilibrium. So this is the amount in moles of what? Of the reactants. The reactants or products were now at equilibrium. At equilibrium. You know what I'm saying? And for for high school students, normally they give you moles and stuff. They give you the amount. But if you are given concentrations, then definitely that's you can work with that as well. And then the last E there is going to be the concentration, right, of the reactant or product of the reactants or the products were at equilibrium, right? So basically now you have gotten your number of moles, and if you are given amount in moles, you are going to be given volume, right? And so to get this E, the concentration, remember it's what? It's the number of moles divided by what? Divided by volume, right? So, and take note, guys, volume is in decimeter cubed. So, and take note that 1 decimeter cubed is equals to 1 liters. Take note of that, And so now, the value that you get from here, that is what comes to the second E, right? And then we're going to calculate this thing and substitute. Then from there, we can go to the equilibrium Kc expression and then substitute the values and get our unitless result, And take note, if Kc is equals to 1, what does that mean? If Kc is less than 1, what does that mean? If Kc is greater than 1, then you can sort of check as to what exactly does that mean. So I am going to do, an exam type question that shows this step by step. And then after, I'm so excited. I want us to look at Le Chatelier's principle and apply it to situations like this. In a reversible reaction, already the rate of the forward reaction equals to the rate of reverse reaction, right? And the concentration of reactants and products are constant. So all of a sudden, this system that is in equilibrium is subjected to a change, right? Or there is an external stress, So basically, let's say, for example, you change concentration of one of the reactants, or you change pressure, or you change temperature, that is going to have an impact, right, in equilibrium. So basically, Le Chatelier is the guy that helped us to, understand as to what impact does changing concentration, pressure, or temperature in a system that is in equilibrium is going to have, right? So Le Chatelier is saying that if a system that is in equilibrium, right? So take note, we're referring to a closed system. If a system that is in equilibrium is subjected to a change, what type of change is this? Changing temperature, right? Changing pressure, changing concentration. So Chatelier is saying processes will occur in the system which tend to counteract or to oppose, the imposed change. And I know some of you are like, what in the world is going on, right? So imagine at home, if you made yourself tea, for example, right? You made yourself tea, or maybe you asked your brother to make you tea and they pour 5 teaspoons of sugar. All of a sudden, you're like, what in the world? This is not the tea I ordered, you know? And then for you to counteract that imposed change that someone added to your tea, you're gonna either add more water into your tea, and then it's gonna reach the state you wanted it to be, something along those lines. So basically, a system is in equilibrium, and something happens to this system in equilibrium. Pressure is changed, right? Temperature is changed, or concentration is changed. The system is gonna be like, no, bruh, I'm not about that life. Something is going to happen within the system that is going to actually oppose that change and reach a system back to a new equilibrium. But take note, KC will not change when we are dealing with pressure and concentration. And I'm going to tell you guys more about that as we go further. Okay, number one, let us look at the effect of concentration in a system that is in equilibrium. Concentration. I'm going to have a hypothetical reaction here once again. So let's say we've got A in a gaseous state plus B in a gaseous state. This is an equilibrium reaction which produces C in a gaseous state. Right? Okay, fine. So basically, let's say we increase the concentration of B, for example. We increase the concentration of the reactant. Let's say we increase this concentration. So you're asking yourself, what in the world is going to happen here? So Chatelier is saying, if a system that is in equilibrium is subjected to a change, processes are going to happen within the system which tend to counteract the imposed change. So an increase, right? An increase in concentration of this reactant will shift equilibrium to the right. So the forward reaction is going to be favored. So now this is very important. When the forward reaction is favored, what implication does that have? It means that, I'm going to write this in green. It means that all of a sudden, the concentration of A is going to be reduced. The concentration of C is going to increase. Why is this happening? This is happening to counteract the change which occurred. You know what I'm saying? So increasing the concentration of B is going to favor the forward reaction. Increasing the concentration of a reactant, right, is going to favor the forward reaction. So what I'm saying, increasing the concentration of a reactant is going to shift equilibrium to the right. Is going to shift equilibrium to the right, hence favoring what? The forward reaction. Favoring the forward reaction. Right? And I want you guys to take note that where equilibrium is shifting from, right, there is what? there is a reduction, and where equilibrium is shifting to, there is an increment in those substances, right? So now I'm asking you, what is going to happen if I, let's say, increase the concentration of A? If I increase the concentration of A is still a reactant. So equilibrium is going to be like, okay, the concentration of A is increased. Equilibrium is going to shift once again to the right, towards the product side. And the forward reaction is going to be favored. So as a result of increasing the concentration of A, what is happening is that the concentration of B is going to decrease. Equilibrium is shifting from the right. The concentration of C, which is the product now, is going to increase. So what happens, guys, when we decrease? Let's have this one here. What happens when we decrease the concentration of, let's say, concentration of A, for example? Let's decrease the concentration of A, and take note that we've got A plus B. It's an equilibrium reaction to give us C. These are all in gaseous state. So when this happens, equilibrium is going to shift to the left, right? So reducing the concentration of a reactant is going to shift equilibrium to the left, favoring the reverse reaction. So what am I saying? Reducing the concentration of a reactant is going to shift equilibrium to the what? To the left. Is going to shift equilibrium to the left, favoring what? Favoring the reverse reaction. The reverse reaction. Take note, where equilibrium is moving from, there is going to be an increment, right? Where equilibrium is shifting to, there's going to be an increment. So where it's moving from, there is going to be a reduction. Where it's moving to, there is going to be an increment. So what has happened here? We reduced the concentration of A, right? And since we reduced the concentration of A, equilibrium shifted to the left, and hence the concentration of B is going to increase, right? What is going to happen to the concentration of C? The concentration of C is going to decrease. Sorry. The concentration of C is going to decrease. Yes. Okay. Excellent. So basically, in a nutshell, I'm saying that if you reduce the concentration of a reactant, equilibrium will shift towards the site where the concentration was reduced to increase, right? To bring about an increment, and that seesaw example was such a cool one. You know what I'm saying? So if something is heavy over here, and then you've got a very small thing here, so equilibrium is going to shift this direction to counteract the change that happened. You know what I'm saying? And then let us look at this. A still in a gaseous state, B in a gaseous state, to give C in a gaseous state. What happens when you increase the concentration of C? Remember that this increment of the concentration is happening at a constant volume, right? Take note, volume is inversely proportional to pressure. Okay. Stay with me. Okay, fine. So you increase the concentration of C, right? What is going to happen to equilibrium? Since C is increasing, equilibrium is going to shift to the left, right? when it shifts to the left, what's going to happen is that the concentration of A and the concentration of B are going to what? Are going to increase, as a result of equilibrium shifting to the left. So now the reverse reaction is going to be favored. The reverse reaction is going to be favored. Is going to be favored. Okay, so what happens when you reduce the concentration of C? So when the concentration of C is being reduced, right, equilibrium is going to shift to the right. So equilibrium is going to shift to the right, right? So what is happening there? When it shifts to the right, what happens to the concentration of A and B? So concentration of A and concentration of B are going to what? They are going to be reduced, and then C is going to increase. Concentration of C is going to increase. So let's summarize this. When the concentration of a reactant, is increased, what is going to happen is that equilibrium is going to shift to the right because the concentration of the reactant is increased. What effect will this shift have in the reaction? So the other reactant concentrations are going to decrease, and then the product concentrations are going to increase, right? And then the opposite is true, that when the reactant concentration is reduced, what is going to happen? What's going to happen is that equilibrium is going to shift towards the side with the reduced concentration. And what effect does that have? So if the reactant concentration is reduced, this means that all of a sudden the reactant concentration is going to be increased and the product concentration is going to be reduced. In a constant volume, this is what is going to be happening. And also, what happens when the product concentration is increased? If the product concentration is increased, equilibrium will favor what? The reverse reaction. The reverse reaction is going to be favored. So what impact does this have in the other substances? So the reactant concentration is going to be increased and then the product concentration is going to be reduced, right? So that is what is happening basically. And also, what happens when the product concentration is reduced? Where in the world will equilibrium shift to? Equilibrium will be shifted to the right, right? And when that happens, the reactant concentration is going to be what? It's going to be reduced and the product concentration is going to be increased. Why is this happening? It is happening because Chatelier said, if a system that is in equilibrium is subjected to a change, then the processes here are the shifting of equilibrium, the increment of concentrations, right? Processes will occur within the system which opposed the change that took place. Okay, a system that is in equilibrium, that is subjected to a change being an increment in temperature or increasing temperature or reducing temperature, what is going to happen? There are going to be processes within the system that are going to counteract, that are going to oppose that change, right? So before I can sort of take you guys through the effect of temperature, the effect of changing temperature in a system that is in equilibrium, I want you guys to take note of, let's take it back to the earlier grades, right? You guys have been exposed to exothermic reactions. Remember when you guys were doing, when you had your combustion reactions were highly exothermic reaction where the change in enthalpy was less than zero. In other words, the change in enthalpy was negative. So, exothermic reaction, these reactions releases energy, right? And also, you guys learn about endothermic reaction. You learned about endothermic reactions, and endothermic reactions are characterized by the change in enthalpy being greater than zero, or the change in enthalpy is positive, right? And endothermic reactions are reactions which absorb energy, right? And so now I'm going to take you guys through this as to what effect does temperature have, and how will the system react or behave when temperature is changed. So let's go back to our hypothetical reaction once again. So let's say we've got A in a gaseous state plus B in a gaseous state, and then we are forming C in a gaseous state. And then this reaction is, let's say, exothermic, right? Okay, cool. So now, I want you guys to know, right, that the change in enthalpy that is written here is for the forward reaction. This is for the forward reaction, and obviously the reverse reaction has got a change in enthalpy which is greater than zero. This will be for the reverse reaction, right? Let's say again we've got D in a gaseous state plus E in a gaseous state, and then we are getting here F in a gaseous state. And then you are told that the change in enthalpy is greater than zero, right? So this is an endothermic reaction, you see? And so basically this is for the forward reaction, and then the reverse reaction, so the reverse reaction being F here to form E and D. So the change in enthalpy is less than zero. So the forward reaction is endothermic, the reverse reaction is exothermic, right? Okay, so basically increasing temperature increasing temperature, what did I even write? Increasing temperature favors, what do you think that favors? Increasing temperature favors the endothermic reaction. So an increment in temperature favors the reaction that absorbs energy, right? So a reaction that decreases the temperature of the system. So remember, something happened, you increased temperature. So now processes are happening within the system to reduce, right, the temperature. So increasing the temperature is going to favor an endothermic reaction. It's going to favor the reaction that absorbs energy, right? And decreasing temperature is going to favor an exothermic reaction. an exothermic reaction. So a reduction in temperature is going to favor an exothermic reaction. It's favoring the reaction that releases energy, right? A reaction that increases the temperature of the system. Okay, cool. So basically, let's look at our equations here. Let's look at our reactions. Let's look at the first one. I'm going to use blue here. With that knowledge, let's look at this one. So let's say here we increase temperature. Where will equilibrium shift? We said an increment in temperature is going to favor a what? An endothermic reaction. So as you can see here, the forward reaction is exothermic, right? And so an increment in temperature is going to favor the reverse reaction. Why is that the case? Because the reverse reaction is what? The reverse reaction is endothermic, right? If you decrease temperature, equilibrium is going to favor the exothermic reaction. So the forward reaction here is exothermic. So basically, let's look at the second equation. If we increase temperature in this equation, right? What is going to happen? The forward reaction is endothermic reaction. So if we increase temperature, what's going to happen is that equilibrium is going to favor the endothermic reaction. So the forward reaction is going to be favored, right? And what happens when you reduce temperature? When you decrease temperature. So when you decrease temperature, what is going to happen is that equilibrium is going to favor the exothermic reaction. So for this second reaction, the reverse reaction is exothermic. How do we know that? So whenever they write a reaction for us in this fashion and right here the change in enthalpy greater than 0, that is for the forward reaction, and automatically this is for the reverse reaction. So an increase in temperature favors the endothermic reaction, and a reduction in temperature is going to favor the exothermic reaction. So a system that is in equilibrium, right, where the rate of the forward and the reverse reactions are equal, right, and the concentration of the reactants and the products are the same, if that system is subjected to a change, and the change in this case is either increasing pressure or reducing pressure. And before I can dive, deep into this, I just want to, remind you guys of what you learned in earlier grades, that pressure is inversely proportional to volume, right? So what this means is that when you increase pressure, volume decreases, or when you decrease pressure, volume increases, right? So now we are saying this system is already in equilibrium. The rate of the forward and the reverse reaction are equal. The concentration of the products and the reactants are constant. All of a sudden, we increase pressure. How will that go about? So first and foremost, this is applicable when we have got our substances in a gaseous state, right? That's where pressure is applicable. So an increase in pressure, right, is going to favor the reaction, right, that decreases the number of gas molecules. That decreases the number of gas molecules. Okay? Or rather, if you increase pressure, take note, pressure inversely proportional to volume, right? an increment in pressure, volume is decreasing. So if you increase pressure, you are going to favor, you're going to favor the reaction, you're going to favor the reaction that form smaller or fewer amount of gas, right? Or you're going to favor the side that form less gas molecules, right? You're going to favor the reaction that form smaller gas molecules, or rather the side that form less gas molecules. So let us look at the reaction that we have. We have got 3 molecules of A with 1 molecule of B, right, in our reactant side. And then we've got 2 molecules of this molecule right here. So on the reactant, in total, what we've got 4 gas molecules. On the product, what we've got how many? 2 gas molecules. So what does that mean? It means that equilibrium now is going to shift to where? It's going to favor the reaction that reduces the number of gas molecules. So it's going to favor the forward reaction. Why is it favoring the forward reaction? Because the forward reaction is the reaction that decreases, right, the number of gas molecules. You know what I'm saying? So take note, our molar ratio here is what? It's 3:1, and then our product side is 2. So on the reactants, we've got what? 4 gas molecules. On the products, we've got 2 gas molecules. And increasing pressure, right, is going to favor the reaction that decrease the number of molecules. You know what I'm saying? The number of gas molecules, and that is the forward reaction. Okay? And what happens when you decrease? If now you decrease pressure, so decreasing in a pressure, right, is going to favor the reaction with more gas molecules, or the reaction that produces, or the reaction that forms more amount of gas, or the reaction that forms more amount of gas. So this here was favoring the forward reaction, right? So now, as we just noted, that on the reactant side, we've got 3 molecules is to 1 molecule there. And then on the product side, we've got 2. So now you decrease pressure. Pressure inversely proportional to volume. Volume is increasing. So this is going to favor the reaction that forms more gas molecules. So what is going to happen is that this is going to shift to the left. The reverse reaction is going to be favored, right? Okay, sure. So in general now,